So let's do number 1 of this assignment together. So follow along. First thing, well, let's read the instructions. We got a motion detector. That's just a machine that lets us record the position and the velocity of objects as a function of time. In this case, we're using it to measure velocity. And we have an object that's rolling down an incline, and we record these data. Every second, it records the velocity of our object as it rolls down. First thing we're going to do is we're going to graph the velocity versus time graph. Then we're going to write a math model for the velocity as a function of time. Then we're going to use the area under the velocity versus time graph. And we're going to write a data table for the position of the car as a function of time. And we're going to assume that our starting position is at the origin, at 0. And then we're going to graph that position versus time graph. And we're going to make this graph really big and really neat. So I might have to have somebody, could you get me a ruler? Just put it right here. All right, so let's get started. So number 1. And first thing I want you to do is write down what's given. And here's our time in seconds and velocity in meters per second. And I'm going to make another column over here. And this is going to be for x in meters. Now that's later on when we actually make some calculations. So we've got 0, 1, 2, 3, 4, 5 seconds. And our velocity is 0, 3, 6, 9, 12, and 15. And I think you can see here that we're increasing the velocity at a steady rate. Every second, we're increasing our velocity by 3 meters per second. So for part A, it says graph this. So let's do that. Now this graph can be fairly small. So we're going to go from 0 to 15. So I'll just go 2, 4, 6, 8, 10, 12, 14, 16. So this is velocity, meters per second. Always label. And then 2, 4, wait, I'm sorry, 1, 2, 3, 4, 5. So this will be time in seconds. And then we'll just graph these. At 0, it's 0. At 1 second, it's 3. So 2, 4, 6, 8. Oh wait, I'm sorry. What did I want that to be? This, shoot. So this will be 2, 4, 6, 8, 10, 12, 14, 16. That's what I meant to do. So at 1 second, it'll be 3. So I plotted that right. At 2, it'll be 6. 2 seconds, it'll be 6. And you can see this is going to line up nicely. At 3, it's going to be 9. At 4, it's going to be 12. And then at 5, it's going to be 15. So 15 will be right there. And we just connect all those data with a straight line. So that's part A. Now part B, it says write a math model. So, okay, y equals mx plus b, whatever. The y-axis is v. The slope, I think you can see that every second we're going up by 3 meters per second. So the slope is 3 meters per second every second. If you want to write 3 meters per second squared, go for it. And this is times time plus 0. At time t equals 0, the velocity is 0. And you can just put plus 0 or you can just leave it alone. So there's our math model for velocity. Then it says, for part C, it says using the area under the velocity versus time graph, write a data table for the position of the car as a function of time. Now I'm going to do it a little bit differently than I did in the video, because this will work no matter what the graph looks like, what the velocity graph looks like. Look at 1 second. What's the area of this little triangle? Well, it's 1 times 3, base times height divided by 2. 1 times 3 is 3, divided by 2 is 1.5. So, well, first of all, at 0, the position hasn't changed yet. And we can really call this delta x, that's fine. But at 1 second, we've increased our velocity to 3 meters per second, but we've only had a chance to go 1.5 meters, 1.5 meters. Okay. And then at 2 seconds, now watch this. This is where people mess up. This is why I'm actually recording this and doing it now for you, because last period, everybody was making the same mistake. So I don't want you to make that mistake. So you might think, oh, okay, well, let's do the same thing. But now we have this little triangle like this, but we also have this rectangle. Well, what's the area of this little rectangle? Well, it's 1 times 3, right? It has a height of 3 meters per second. So 1 second times 3 meters per second is 3. So this is 3 meters right here. And then it has a, well, what is this triangle? Well, it's 1.5. I'll go ahead and put the 1.5s in there. Now, what total distance have I gone? I mean, what's my displacement now? Some students will say 4.5, and they're partially right. 4.5 meters is how much you added to your position since the end of the first second. But I don't want how far I added. I want to know how far I went from the beginning. So what do I have to do to that 4.5 meters? Add the 1.5. See, what you have to do is add the whole thing. So 3 plus 1.5 is 4.5, plus the 1.5 I started with. So that's 6.0 meters. And we're going to do the same thing here. Now let's break it into a rectangle. Now what's the area of this rectangle? Well, it's 1 second times 6 meters per second. That's 6 meters. And then the triangle, what is the triangle again? 1.5. So here we've added 7.5 meters to our position between the second and third second. Between here. But I have to add that to the 6. So what do we get? 13.5. And then we do the same thing here. Now this is 9 meters per second times 1 second. It's 9 meters. So that's 9 meters right there. Plus the 1.5 meters I have to add because I'm accelerating. So this is 10.5. Added to 13.5, you get 24.0. Now, let's take a look at this one. For the last second, at 5 seconds, between 4 and 5 seconds, how much do I increase my position? Well, this rectangle is 1 second times 12, so that's 12 meters. And then I have to add the 1.5 meters to that. So that's 13.5 plus 24 is 37.5. Is everybody with me on how I was doing that? Now this kind of makes sense also. Check this out. Do you see that this is one big triangle? What's the area of that triangle? That's my total displacement. 5 times 15 is 75, but it's a triangle, so 75 divided by 2 is 37.5. Bingo. Okay, we did it. Now what we need to do is graph this. We need to graph delta x as a function of t. But it also says in the instructions that the initial position is 0, so we can just call delta x, x. But I need this graph to be big and neat. I want it to take up half the paper here. Let me zoom out a little bit. Okay, so that's what I'm going to do. I'm going to pick an origin right here. I'm going to draw my horizontal axis. And if you want to get up right now and quietly get a ruler, you can do that. And make my vertical axis. Now I would say each problem should get its own page in your notebook. So, you know. Now, so this will be time in seconds. Now it only goes for 5 seconds, so we can really space this thing out. You know, 1, 2, 3, 4, 5. Okay, so there's my horizontal axis. It's the whole width of this paper. Now, what is x? Okay, this is going to be x in meters, and I want to go from 0 to 37.5. Wait a minute. Just round that up to 40. Just go from 0 to 40. It's easy to come up with something it's easy to scale this for 40. So if I make this see 1, 2, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll make that 20. I'll make this 10, 20, 30, 40. See, now it'll fit really nice on there. And this is a skill you'll develop. The more you graph, the more you'll get better at this. Now, so each one of these is 2, 2, 4, 6, 8, 10. So at 0, we had 0. Now at 1 second, we only went up to 1.5. So where's 1.5? Well, here's 1, because this is 2, so there's 1. 1.5 would be right about there. And then 2, at 2 seconds, we're all the way up to 6. So 2, 4, 6. And then at 3 seconds, we're all the way up to 13.5. So 12, 13.5. Right there. And then at 4 seconds, we're at 24. And then at 5 seconds, we're at 37.5. So 32, 34, 36, 37.5 is right there. Now I've plotted my points. Now I'm going to draw the graph. Now this is a smooth curve. This is a parabola. So we want to make it really smooth. So I start off kind of like this. And this, you just kind of do the best you can to make it nice and smooth, going through all the points. Look at that. That's a good job right there. And it has to be this big, okay? Because here's what we're going to be doing on the next assignment. We're going to be taking tangent lines to this. We're going to draw a tangent line to this, tangent line to this, and so on. And so to figure out instantaneous velocities. I'm going to cover all that on Monday next week. But if these aren't beautiful, if these position versus time graphs aren't big and neat and wonderful, you're not going to be able to do assignment 2. So when I check assignment 1, if these graphs aren't big and beautiful, you're going to have to redraw them as part of assignment 2, which will take a lot of time. But anyway, this we are done. This is part D. drawing this graph. So we have done it. We have done number 1 completely. Now, number 2 and number 3 are going to be a little bit different, but it's the same idea. You're just doing the same thing, even, and if you have trouble with that, ask me. Okay, I think that's enough. All right, that is all.